Next up, we've got Alan Scarborough, the Corrosion or Commercial Metals.
Very good. Thanks for the opportunity to be here. It's a real pleasure to be a part of this discussion about corrosion, and I'm going to brief over some of the elements that rebar and how reinforcement can contribute towards the goal of a 100-year life cycle. And just real quickly about CMC is, a lot of you may be familiar already with the recycling facilities that are around the country, but CMC also has fabrication and several different mill products that are milled throughout the country. But there's been a recent acquisition that I wanted to mention, that it's a new division of CMC, which is the Tensar Corporation. And also CMC is very well aligned in order to provide resourceful products that are sustainable. And the reinforcement products that we're going to go through in this briefing, this just kind of gives you a quick snapshot of or scalability about where they're located. We're going to talk about Chromex technologies, which are manufactured in Casey, South Carolina, and then on the west side, on the west coast in Oregon. And then there's a coatings facility that will be part of this discussion. It's located in Tulsa, Oklahoma. So the market options, it's there's a lot of different durability elements related to each one of these systems, so we'll try to outline those. For uncoated materials, there's stainless steel, which will go through the ASTM A955 process for that. There's the low carbon chromium products, which is A1035, and then as far as coated products, we'll look at the epoxy coated technology, some dual coated technologies, and then also some different classifications for galvanized coating materials. So to get started with the uncoated material, this is just an AASHTO rebar table that shows the most common that we see. There's 2304, which contains up to about 24.5% of chrome and up to about 5.5% of nickel, and then the molybdenum is between 0.05 to 0.6 in steel chemistry. And so regrettably, some of us may recall that this was a pretty recent supply network challenge that we encountered with this technology. And so that increased a lot of cost. It developed a lot of turmoil in the industry, where there had to be projects that were converted to different technologies. And this mostly because there's only one mill in the U.S. for stainless steel. And then the other challenge is we're limited with fabrication feasibility as well. So that created some real supply chain problems in the past year. And then also listed on this AASHTO rebar table are the chromium alloy steels, and that's your ASTM A1094, which is K81550, and it's got about 50% less chrome in it, and it has no nickel or no moly related to this product, and it meets or exceeds all the mechanical properties of ASTM A615, and as far as grades 80 and 120. But the main thing is it has, and you may already be familiar with this product, but it has 3 different ASTM classifications. You see in the orange down here that the 2100 or the 2000, it's up to about 4% chrome. 4100 is up to about 8%, and then 9100, which is the most commonly used because it has the best corrosion resistance. It's up to about 10.9, but it's classified as 9100. Just recapping, this is the map overview again, just showing the 2 supply locations on the east and west coast. And I mentioned earlier, we've been seeing a pretty significant trend of a lot of these stainless projects that have been converted to Chromex or other technologies that are in the industry, and in some cases you see A955, 2304 as a top mat solution, and then they've applied the 9100 on the bottom mat. And it's not only due to some of the supply chain issues, but there's also some logistical benefits that are related to 1035 that it can be fabricated by any fabricator or any independent fabrication shop or any of the mill fabricators. It's not limited to just 3 different fabrication locations around the country. And this just gives you an economy of scale. Again, you see the content for chromium in stainless steel. And the thing to keep in mind is it was originally innovated as a corrosion resistant material for architectural applications, for tank corrosion resistance, and kitchen equipment, and just like facades on buildings and stuff. And so that's 95% of what we see and used in today's industry. And the Chromex, or the 1035 CS product, it was developed specifically to passivate in concrete and to be used as dowels in pavements. And you know, one of the things too is the raw materials are a little volatile with stainless, and they also are with Chromex. But one of the things that the contribution that it makes is it's about 35 to 50% reduced cost over the stainless steel product. So that's another part of what we'll be talking about throughout the day is just some of the cost variables and comparisons. Getting into some of their research, in 2019 they had a paper that was by the University of Akron where they saw a lot of they did some bond strength testing and saw that they had greater results than stainless steel. And some of the other elements that we see here is in terms of chloride threshold. 1035 is 2500 ppm, and that threshold is about 15% of what carbon steel is. So it's a massive improvement over what you experience with carbon steel. And then as far as crack width or crack quantities, the A955 experiences 30% more cracks. And so by reducing the cracks, you're able to keep the concrete matrix and surface healthier. Getting into the coated materials, we'll start with galvanized, which there's 2 standards. There's A1094 and 767. We'll start with the continuously galvanized reinforcement, which this is produced with an automated process. It's still hot dip galvanized at 830 degrees, but it's very similar to the hot rolled steel coil sheet process that maybe some of you have been in one of those really innovative facilities where they make steel coil for the automotive industry. And the key thing with this material is it can be fabricated after it's been processed. So there's some logistical advantages there. And then the batch process is one that we've seen for a long time. There's 2 classifications for it. It's A767. And most commonly, the predominant classification that we see used in this product is Class 1, which is a little bit thicker coating, but keep in mind that the typical thickness is about 3.4 mils. You know, in the continuous it's 2 mils, and I'll show you a slide on that in just a second. Comparing principles, this is epoxy on this graphic, just showing the basic principle that this is an impermeable barrier application, but it's adhesion dependent, of course. And in the middle you see the galvanic series of metals. There's actually a good workshop tomorrow in Section 8 that I'm looking forward to attending myself. It'll kind of go through some of this system as far as the cathodes and the anodes. In this sense, any of the metals that are above will protect the metal below in the order. So zinc, you see, is well positioned to protect steel and to serve as a sacrificial anode. And in addition to that, in addition to a barrier protection, this is providing 2 to 4 times the corrosion resistance, delaying corrosion for the underlying steel, but then also not only is it in a good position on the galvanic series of metals, but it's well suited for a variety of harsh environments to also provide better corrosion resistance. This is a cross section just showing you the 767 standard. It's on your right side, and then the continuous is on this side. And one of the things to take note here is in a batch operation, the bars are submerged into a zinc bath, and so the reaction occurs, and depending on the steel chemistry, you have layers that build up, and this top layer averages between 10 to 40 microns, and that's the part that gives you the most value for corrosion resistance. And of course it diminishes, and actually the hardness scale, as it gets closer to the substrate, increases. So you have some variables as far as hardness, ductility, and amount of zinc. So it's an unpredictable situation, what's going to happen whenever it's being fabricated, or if you have a area that peels. And there's a repair method for that if it does occur. But this technology was innovated to address that situation. So what you have in this case is a 50 micron minimum coating. It averages about 65, but it's a pure zinc layer. And so you have a consistent ductility, and so that's what enables it, I mentioned a little earlier, to be fabricated after it's been coated. Just a quick graphic on how galvanizing works. You have this initiation phase where the chlorides are coming into the concrete matrix, creates the cracks, and then you have a propagation that occurs after the passivation breaks down, and it's able to increase, oxides start growing on the metal, and that'll create the spalling after the volume is increased. And so whenever you have zinc on the zinc coating, what occurs here is once the critical chloride threshold is met, then you have these zinc ions that are migrating away from the matrix, and they're less voluminous, and so they're going to infill those pores, and actually densifies the concrete. So it has a positive consequence there. It's a more homogeneous coating. As I mentioned, the 767 is unpredictable how thick that coating might be, or how easily it's going to be to work with. In addition to that, it's an efficient use of zinc. You're not getting a combination of materials, and it also impacts cost because the conventional method charges based on how much material they put on the metal. With continuous, you charge based on just the weight of the metal. And so this has all resulted in improvements in protection. As far as bond strength, may have mentioned that already, but you see this is a excerpt from a University of California study. There was over a 12-month period, and they did 3 measurements, one at 30 days, 90 days, and another one at 1 year. And what you see happening here is the galvanized material, as it's curing, that bond strength is actually improving, and it's the slip resistance is superior to not only the epoxy coated rebar, but also conventional rebar as well. This is a 100-year design life analysis. This is an excerpt from the University of Kansas study that was conducted by Dr. David Darwin, and it was released in 2021. But the key thing that we found here was he was looking at the average cost of bridge deck materials this was funded by Oklahoma DOT. And so you have conventional up here on a 8-inch deck, and so you have 2.5-inch cover, and then this is an 8.5-inch deck with a 3-inch cover. And so with conventional on the 3-inch cover, they're estimating that at year 100 you would have 3 repairs, and the cost would be just south of $800, just north of $900 on the 2.5-inch deck, and you'd have 4 repairs. This is the epoxy coated material, and so you're showing 2 repairs with a cost of just north of $500. And whenever you have an extra 1/2 inch of cover, that is reduced down to 1 repair with a cost of just south of $400. And then these 2 down here, this is A767 and 1094. He applied the same corrosion rate to both of these technologies respectfully, even though the 1094 is going to corrode at a slower rate. But in this scenario with a 2.5-inch cover, you got 2 repairs, and these costs are less. They're just south of $500, and then he assigned the 1094 as the lowest cost. And same thing down here. You got a little bit extra as far as 1 repair within the first 100 years. 367 and just north of 350 on the cost that they applied there. We'll talk about the dual coating systems now and what are the available substrates. You got the same standard carbon steel with 615 and 706, as well as 1035. And as far as putting a 1094 coating on steel, this is just a graphic. I've got a good video if anybody wants to stop by the booth to see this process, the automated process in motion. But this can be applied to all these substrates. You can apply galvanizing to any grade steel as well. And so you got these substrates over here. This is more of an intermediate substrate. And so there's an ASTM standard that's A1055, which is where you would apply the fusion bonded textured epoxy coating for top coat with either 775 or 934, and then 1035, ASTM 1035 or the Chromex, either in any of the standards they have in the ASTM standard that you can apply a galvanized coating on top of that. And that's going to give you well over 100 years of service life and compete with anything that you might consider using stainless steel on. And just to kind of look at the benefits of the dual coat, of course, both technologies, they're readily available, and multiple coaters can work on those. There's improvements in the bond strength. That's in testing right now. There's actually a research project that's in progress. You've got durability improvements along with the improved service life compared to the stainless technologies. And the main thing is these technologies are increasing the corrosion resistance through not only the principle of sacrificial coating protection, but also it's using the barrier protection. So you have an enormous amount of redundancy built into that in case there is something that might happen to go wrong, which that never occurs in our industry. And in conclusion, it's not only a highly innovative way to raise performance, but it's a more durable measure. Again, I mentioned redundancy, but I mean that's really the key part here, whether you're coating with an epoxy or with a zinc coating. And then there's a lot of compiled results that indicate that this is a cost-effective way. It's 35 to 50% less than stainless steel to potentially replace stainless steel for a long-term replacement. And then I mentioned that at the Center for Infrastructure Research at Texas A&M University, there's a research study in progress that's looking at the dual coat technology. Touching on sustainability real briefly, we all understand that steel, of course, is the most recycled material in the world, and it can be fully recycled multiple times without compromising its mechanical properties. And just to compare it to other materials like paper, for instance, it can be recycled 5 to 7 times, and plastic can only be recycled 1 to 3 times. The key thing, I mentioned that CMC has 100% recycled technologies, but they apply a scrap-based electric arc furnace steel making process, and so that's what really makes it possible to make these new products out of 100% recycled steel. There's a mill in Seguin that creates 100% recycled materials for the rebar, and this is going to reduce the CO2 emissions by up to 63% compared to what other mill operations are averaging around the country. And this is not only going to reduce that, but it's also going to help with the average energy use by 82%. And that's very, very important to point out towards preserving our natural resources. And I'll close on an exciting announcement that occurred yesterday, that CMC announced that they're going to have rebar zero. And so some of you may have received the notification that they're going to be launching this 100% carbon neutral initiative. But sorry, I don't have more details other than just this slide to mention it. But essentially what it is in addition to that 63% reduction that they have with the renewable resources, they're going to be using carbon offsets and RECs to neutralize those scope 1, 2, and 3 greenhouse emission studies with the production, fabrication, and delivery. That's completely net zero emissions to the job site. So hopefully by the time we gather again, we'll have more information we can share on that, or if you need more details about it, then please let me know. But that concludes the presentation, and again, thank you for this opportunity to contribute to this conversation about corrosion resistance.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.